Spectroscopy is a fundamental scientific technique that involves the study of the interaction between matter and electromagnetic radiation. By analyzing the spectrum of light emitted, absorbed, or scattered by materials, spectroscopy allows scientists to gain insights into the composition, structure, and properties of matter. Light dispersion, a key phenomenon underlying spectroscopy, is essential for separating light into its constituent wavelengths to reveal valuable information about the source or medium. This description delves into the principles of light dispersion, the historical development of spectroscopy, and the diverse applications of this versatile technique in science and technology. Understanding the principles of light dispersion helps to appreciate the advancements spectroscopy has brought to fields ranging from astronomy to medicine. The origins of spectroscopy can be traced back to the 17th century when Isaac Newton conducted his groundbreaking experiments with prisms. Newton discovered that white light could be separated into a spectrum of colors, demonstrating that light is composed of multiple wavelengths. This phenomenon, known as dispersion, occurs because different wavelengths of light refract at slightly different angles when passing through a medium like a prism. In the early 19th century, Joseph von Fraunhofer introduced the use of diffraction gratings, improving the resolution of spectrometers and enabling the detailed study of spectral lines. These lines, now known as Fraunhofer lines, correspond to specific wavelengths of light absorbed by elements in the sun's atmosphere. Fraunhofer's work marked the beginning of modern spectroscopy, linking light dispersion to the study of atomic and molecular structures. Further advancements came with Gustav Kirchhoff and Robert Bunsen, who developed the principles of emission and absorption spectroscopy. They demonstrated that each element has a unique spectral fingerprint, allowing for the identification of elements in a sample by analyzing its spectrum. Light dispersion refers to the process by which light separates into its constituent wavelengths or colors when it interacts with a medium. This phenomenon occurs because the speed of light varies with wavelength when traveling through a material. Dispersion is governed by several fundamental principles. The refractive index, N, of a medium determines how much light bends when entering the medium. The refractive index varies with wavelength due to the material's dispersion properties, causing shorter wavelengths, e.g., blue light, to refract more than longer wavelengths, e.g., red light. Prisms are classical tools for achieving light dispersion. When a beam of white light passes through a prism, it refracts at both entry and exit points, with each wavelength bending at a different angle. The result is a continuous spectrum ranging from violet to red. The angular separation between colors depends on the prism's material and geometry. Diffraction gratings, consisting of closely spaced lines etched on a surface, disperse light by interference rather than refraction. When light interacts with a grating, constructive and destructive interference occurs at specific angles for each wavelength. Light dispersion can also be influenced by polarization. Polarized light interacts differently with materials depending on their birefringence properties. Anisotropic materials, such as crystals, can split unpolarized light into two orthogonal polarized components, further enhancing the dispersion effect. Spectroscopy encompasses a wide range of techniques, each tailored to specific applications and types of electromagnetic radiation. The following are the primary categories of spectroscopy. In absorption spectroscopy, a sample absorbs specific wavelengths of light, resulting in dark lines or bands in the spectrum. These absorption features correspond to electronic, vibrational, or rotational transitions in the atoms or molecules of the sample. Common types include ultraviolet-visible spectroscopy, which analyzes electronic transitions in molecules, and infrared spectroscopy, which studies molecular vibrations and bond structures. Emission spectroscopy involves analyzing the light emitted by a sample when it is excited by an external energy source. The emitted light reveals the energy levels of the atoms or molecules. Examples include atomic emission spectroscopy, used to identify and quantify elements in a sample, and flame photometry, a subset of atomic emission spectroscopy used for metal analysis. Raman spectroscopy relies on inelastic scattering of light, where photons interact with molecular vibrations, resulting in a shift in wavelength. This technique provides information about molecular structures, functional groups, and chemical environments. Nuclear magnetic resonance spectroscopy examines the interaction of atomic nuclei with radio frequency radiation in the presence of a magnetic field. It is particularly useful for elucidating the structures of organic compounds and biomolecules. X-ray spectroscopy investigates the interaction of X-rays with matter, including absorption, emission, and scattering phenomena. Techniques such as X-ray fluorescence and X-ray photoelectron spectroscopy are widely used in material science and surface analysis. Spectroscopy has revolutionized numerous scientific disciplines and industries. Its applications span from fundamental research to practical problem solving, including astronomy, where it is a vital tool for studying celestial objects. By analyzing the spectral lines of stars, galaxies, and nebulae, astronomers determine their chemical composition, temperature, velocity, and distance. Spectroscopy also played a crucial role in the discovery of exoplanets and the expansion of the universe. In environmental monitoring, spectroscopic techniques detect and quantify pollutants in air, water, and soil. For example, absorption spectroscopy measures greenhouse gas concentrations, while fluorescence spectroscopy identifies trace organic compounds in water. In medicine and biotechnology, spectroscopy aids in diagnostics and treatment monitoring. Infrared spectroscopy identifies biomarkers in blood samples, while NMR spectroscopy helps determine the structures of complex biomolecules like proteins and nucleic acids. Raman spectroscopy is used for non-invasive cancer detection. In material science, spectroscopy is indispensable in characterizing materials. Techniques like XPS and Raman spectroscopy provide insights into surface chemistry, crystal structures, and mechanical properties, guiding the development of advanced materials for electronics, energy, and aerospace. Chemical spectroscopy ensures quality control in industries such as pharmaceuticals, food, and petrochemicals. Techniques like mass spectrometry and UV-Vis spectroscopy are used to identify impurities and verify product compositions. Despite its versatility, spectroscopy faces challenges, including improving the sensitivity of spectrometers to detect weak signals, developing portable spectroscopic devices for field applications, and managing and interpreting large datasets generated by high-resolution spectrometers. Future advancements in spectroscopy may include integrating artificial intelligence for automated data analysis, enhancing spatial resolution for nanoscale imaging, and exploring new regions of the electromagnetic spectrum for novel applications. Spectroscopy, underpinned by the principles of light dispersion, is a cornerstone of modern science and technology. By unraveling the mysteries of light-matter interactions, spectroscopy provides a window into the fundamental properties of the universe. From deciphering the compositions of distant stars to diagnosing diseases at the molecular level, spectroscopy continues to push the boundaries of human knowledge and innovation. Its ongoing evolution promises even greater contributions to science and society in the years to come.